In section 4, we're going to deal with finding the volume by using shells. So what we'll do is we're going to take the following. We're going to take a section of a graph just like this right here. Okay, so take this piece, and what we're going to do is we're going to revolve around the y-axis, but we're going to use a different method than what we did before. So again, we want to take and we want to revolve around, okay, and we're going to create a solid by doing that. So if you see this guy right here, as we rotate around, so as we take this curve and we rotate around the y-axis, we end up with this solid. Okay. So what we have to do is we have to come up with a formula, a way to set this up. Okay. So this is kind of cool how it's done. What we're going to do is we're going to take a little chunk of this. Okay, so just one piece of it. You'll have to excuse my computer. Every once in a while, on the first recording, it likes to glitch. Okay, I think we're back. So what we're going to do is this little piece right here, we're going to rotate around, we're going to follow it, okay? So as we rotate around, you see how that traces out a little cylinder. Okay, so we've got this cylinder that gets traced around. But we're going to do a whole bunch of those. Watch. As I change my x value, okay, so let me go back. As I change where this piece is in here, that changes the size of the cylinder. Watch. So let's change that. Notice as we come out, okay, we have a real, it's a flat cylinder, but has a much greater circumference around. As we come back in, we get these cylinders. So what we want to do is we want to add up all of these cylinders together, and if we add up all of those cylinder volumes like that, we'll come up with the total volume here. Okay, so you get a picture. There's a whole bunch of cylinders in here that are added together. Now what's cool about what we're going to do next is if we take this thing right here and we unwrap it. Okay, so I've revolved it all the way around, but if I were to unwrap it and lay it flat, okay, so let's go ahead and show you that right here. As I take this piece and I wrap it, okay, see that? This length right here, if I flatten it out, it's this piece right here, okay? So what I'm doing is by going all the way around, I'm creating essentially just this long kind of board-looking piece here, or a slab, a rectangular piece that's coming out. Now to calculate the volume of this piece, which is the same as calculating the volume of this, what I need to do is I need to figure out how long is the piece, how high is the piece, and then how thick is the piece. Okay, so let me go ahead and draw that out for you. The piece, when it comes back out, I'll exaggerate it. Okay, so it looks something like this. The length of this piece, its length, okay, if I go back to the animation, the length of the piece right here is given by finding the circumference around here. So how do we get the circumference? Well, circumference, so of that, I've got that circle coming around, and it's an infinitely thin piece. We'll talk about that in a minute. But the circumference coming around on the inside is going to be approximately the same thing as the circumference coming around on the outside. So we're just going to take it to be one circumference, okay? So just one circumference around. Now, this circumference, this length coming around, is this exact length right here on our board. So again, if I come back here, this length around is the length coming down here. So how do we calculate it? Well, to calculate circumference, that's equal to 2 pi times the radius. So what I need is, I need the radius out. Well, what is the radius? Let's go back here and look at the animation. The radius out is from here to here. It's this distance right here, okay? And so this distance, we call it x, x sub k star, okay? But it's just any of the x values. So whatever x value I come out to, that right there is the radius out, okay? So our circumference is equal to 2 times pi times however far out we came for the x value, okay? This is the length out. Now, what are the other dimensions that we need? Well, we've got the length now. The length of it is 2 pi x. What is the height of it? So let's go back and look at our picture. Well, the height is this height right here, and that height is given by the function at whatever that x value is. So the height here, this length, is the function at the specific x value that we're looking at, okay? That's this guy right here. So the function evaluated that. And what is the width? Well, the width is the thickness of this guy. And the thickness of this guy, as we become really large, we're just going to call it, and what I mean really large is as we put an infinite amount of these cylinders in there, it'll be, we'll call it delta x, but that'll approach dx. Okay, so this will be dx because it'll be infinitely small as far as the width is concerned. So what do we have? Well, in general, the volume of this guy, which is the volume of this cylinder here coming around, if I take a look here at this volume right here, this total volume will be equal to the base times the length times the height. So the volume of one of the cylinders will be 2 pi times x times f of x times dx. So I just multiplied those three pieces together. And if we add those up from where we want to start, okay, so let's go back here. So if we're starting at A and going to B for our x values, then that means that we need to go from A to B here, just like that. So what you'll notice is that when you go down here in the book, that's where this guy right here comes from. Okay, so that's the explanation. So now let me give you an example here to work through. Okay, and then so I'm going to do an example, and then I'll let you work example number 1. Okay, so my example will be the following. What I want to do is I want to take the following curve, this curve right here, given by 1 over x squared plus 1. So this guy right here, I'm going to take it from, let's say, x equals 1 to, let's say, x equals 2. So between these two lines right here, I want to take this area inside here, and I'm going to spin it around the y-axis, and so it's going to create some kind of volume. So what I want to do is figure out that volume. Okay, so if I take this chunk right here and I spin it around the y-axis, how much volume will I have? And that's solid. That's what we're looking for. So what we need to do is we need to take our function, which is 1 over 1 plus x squared. We need to use it in this formula. So I'm going to pull the 2 pi out. Okay, so what is our volume? So it's 2 pi. Pull that out because it's a constant. I want to go from 1 to 2. And the reason I'm going from 1 to 2 is if you look at my graph, I'm going from x equals 1 to x equals 2. Just like that. So I want to go from 1 to 2 of x. Now x doesn't change. It doesn't change even regardless of what the function is, because this was the length out. Okay, so we take the length out, okay, which is what I mean by the length out is this piece right here. It's this x, so it stays unchanging. F of x is this guy, so we'll plug that guy in. Doesn't matter whether I do 1 plus x squared or x squared plus 1. And then, of course, so I've got this, I pulled this out, I've got this piece, now I just need dx. Like that. So I have to do a substitution here. So I'm going to find an antiderivative for this inside here. And how I'm going to do that is I'm going to let u be equal to x squared plus 1. This guy right here. So by letting it be equal to that, what I end up with is du is equal to 2x dx. Okay. So what do I get over here? Well, I get 2 pi times, now I've got, here's a 2, here's the x, here's the dx. So these guys put together give me this. So if I take those 3 pieces out, I can replace it with du. So that will be 1 over u, because this is u, du. So now I've got the du's here, but I need to change my limits for my integration. The lower limit was when x was 1. So remember, these are always x equals, or whatever variable you're starting with here with your dx. Okay, so x is 1 and goes to 2. Well, when x is 1, then u is 1 squared plus 1, which is 2. And if x was 2, then u would be 2 squared plus 1, which is 5. So now I just need to solve this guy right here. Well, the antiderivative for 1 over u is the natural log of u. So this is 2 pi times the natural log of u evaluated between 2 and 5. So this will be 2 pi times the natural log, that's my bracket, and it didn't turn out so well. The natural log of 5 minus the natural log of 2. And of course those can be combined to be the natural log of 5 divided by 2. So this is 2 pi natural log of 5 over 2. So what you need to do, you should really take some time to think about why this setup, why this formula makes sense. Because here's the thing, once you understand why the formula makes sense, you don't have to memorize it anymore. You can just visualize what it's supposed to be. Okay? You're taking these pieces out. Right? We're taking this piece here, taking this, unfolding it, putting it along here, and we're generating this guy right there. Okay? So now what I want you to do is take some time and work on this example number 1, and then see if you can set up example number 2. So we're creating shells around the x-axis. Okay, so give example number 1 a try, and then try example number 2.